Okay, I'm going to wrap up chapter 4.5, which is all about graphing in the calculus book, and I'm not going to waste too much time. I urge you to memorize, if you're not good at it, the steps for either polynomial and rational. You'll discover a polynomial is much easier. You should also remember that to help you sketch it, if you know the behaviors of a cubic and the behaviors of a quartic and the behaviors of a power to the 5, you will have a much easier time of it. They always start in a certain quadrant, end in a certain quadrant, depending on the beginning behavior, whether it's positive or negative, of the leading highest degree. This will help you. For instance, cubics can only have one inflection point, and only max of 2 max-min points can only do this. There's my 2 max-mins, and there's my inflection points. They can also cross the x-axis up to 3 times. So they can cross the x-axis up to their degrees. They have n-1 min-max points, and they have n-2 inflection points. That's really helpful to know. They always follow that rule. Keep in mind, you can have a cubic that behaves like this, that technically doesn't have a max or min point, but still has an inflection point. See, that doesn't count as a max min. Although the slope will reach 0, you will find one derivative that equals 0. The second derivative will also be 0, which tells you that's an inflection point. So polynomials are much easier to graph. For asymptotes, remember this. For asymptotes for rational functions, remember this. The vertical asymptotes will be dictated here. The horizontal asymptotes will be dictated by the degrees, which degrees they are. And the x-intercept will be dictated by the top degree equaling 0. And when you do the first derivative, their derivatives are much harder to do here. So you will find graphing these much more difficult. Also follow the rules for what measurements you should take when you do discover the asymptotes. Let's say you find an asymptote here, here, here. Let's say you find an x-intercepts here. You will want to take values to the left of the asymptote, to the right of the asymptote, between the intercepts and the asymptote, between the two intercepts, between the intercept and the asymptote, to the right of the asymptote. And you also want to take plus infinity and negative infinity. You want to find any max points. You will want to find if it crosses the horizontal asymptote, which it can. You will want to find. That's about it. And so you can see it can take a lot longer for rational functions, and it's also why in this chapter I'm not going to do every question as I have in other chapters. So let's get straight to the questions. If degree has 3 of local max, explain how the function's value behave at plus infinity and negative infinity. So for a degree 3, as this one is, it will always start in quadrant 3 and end up in quadrant 1. If it had a negative in front, it would always start up in quadrant 2 and end in quadrant 3, which means you're either going to cross the x-intercept once, twice if it just touches and bounces, or 3 times. And you follow the same rules I just outlined. When it's x to the 4, it always starts in this quadrant and ends in this quadrant, which means it can have 4 possible x-intercepts, 3 possible max-mins, 2 possible inflection points. If it has a negative in front of it, it starts in this quadrant and ends in this quadrant. So if you know the end behaviors of polynomials, it'll help a lot. How many local max or min values? I went through that. Determine the formulas of these vertical asymptotes. Okay. This one factors out to x plus 1 and x plus 3. It does not cancel with the top, therefore the asymptote formulas are at x is equal to minus 3 and x is equal to minus 1. Because those values down here will create a 0, which is impossible. Right here, I can tell you this is not factorable, and I don't believe any factors are imaginary in it, so that means this will probably be a graph that looks like that. And you can usually get a hint of that when the degree up here is smaller than this. If you were to look at their degrees, well, no, that's not a good example, but because it's not factorable, there's no asymptotes possible in the bottom. There's no values of x that will create a 0 down here. This one is x minus 3 squared, which means there's only one asymptote at x is equal to 3. And you can also find where the horizontal asymptotes are based on their values and if they cross x-intercept by making the top equal to 0, etc., etc. But that's not what the question asks. Then they want you to draw these things. Okay. You would discover also with polynomials that either the max-min values are clean or the derivatives are clean. So let's go straight to the derivatives for this one. 3x squared minus 18x plus 15. So that's the first derivative. Notice there's no value for, oh no, there is. Okay, so that's the first derivative. And the second derivative, and make sure that's a square. And the second derivative is 6x minus 18 is equal to the second derivative. Now, if I factor out 3 in the first derivative, I get x squared minus 6x plus 5. And I discover that's got factors. 3, x minus 5, x minus 1. Which means that my first derivative has clean factors. In other words, whatever my max will be, it'll be at 1 comma something and 5 comma something. And it'll either cross the x-axis once, possibly twice, or possibly 3 times. So now that I've seen that the first derivative has clean factors, I'm pretty much sure my x-intercepts will not be clean factors. So I'm not going to waste a lot of time using synthetic division or punching into my calculator f of 1. You can. This is a fast way to see if there are clean x-intercepts. It's called the Factor Theorem. And the remainder on the bottom right, or the y value, should be 0. But you can see quite clearly there is no clean factor, and the numbers start getting bigger and bigger. It doesn't mean there isn't a clean factor, but generally when the first derivative has clean factors, the x-intercepts are not going to be clean factors. So that's a lot of information right now. So right now I'm going to plug 1 into this to find out the max. I get 1 minus 9, so minus 8, plus 15, so that's plus 7, plus 30. So I discover 1 comma 37 is indeed a max. When I put 5 into here, I get, I'll let the calculator do it, but you can do it yourself too. I get 5. So that means the other point, 5 comma 5. I can also see the y-intercept right away. When x is 0, all these disappear, and I get 30. That's a lot of information right there. I also see, when I set my second derivative, I could punch in these values of 1 to see if it's negative and positive, to see if they're max-mins, but I really don't have to, and I'll explain why. The behavior of a cubic says that I must start here. I must go to my first max or min. I must go, well, sorry, the first one's is always going to be a max unless it's slip or slide. I must go down to a min. So that means the first one's always going to be a max. It's impossible to have a min here and a max at the second bump and then still go. That's not how cubics behave. So that means I know I'm coming from way down here, going through the x-intercept relatively close to the y-axis, going through the y-axis at 0, 30, hitting a max point here at 1 comma 37, coming down to what I know now is 5 comma 5 as a min point, so it doesn't cross the x-axis again, comma 5, and going up. I can also find the inflection point by making the second derivative equal to 0, and I discover that when x is equal to 3, That's the inflection point. When I put it into here, I get 27 minus 27. No, minus 81. And so, yeah, I'm just going to put it into here instead. And I discover 21 is the result. So 3 comma 21 is the inflection point. I don't even need the x-intercept because it's not going to be clean. But you could plug in a couple values to see where it roughly happens. So for instance, if I put in f of 1, or sorry, f of 0, I get 30. When I put f of minus 1, I get close to 5. When I get plus f minus 2, I'm way down in the negative, which means it's going to happen just to the left of minus 1. So if I'm going to guess, it's going to be minus 1 point, I don't know, 1, 2, comma 0. Now I'm going to put in all my values here. 0, comma 30. 1, comma 36, was it? I think it was 1, comma 36. 37. 3 comma 21 is the inflection point, and finally the min value was 5 comma 5. There. If I were to connect all these points, if I were to ask, make a table, I could even ask it to connect them. I'm going to make my values a little more readable. There we go. And now I'm just going to turn on the graph. And sure enough, look how close I was on the guesswork, but I mean, it's not amazing guesswork on that. It's at, yeah, it was negative 1.12 roughly, negative 1.13. But look at all those values. Much easier to graph a cubic than other things. Okay, I'm going to go on. I'm not going to do b. You can see that it has 0 comma 3 as a y-intercept, and the first derivative should be pretty clean. I'm going to do just a couple of the first derivatives instead of the graphing of it. So we already have a point, so that helps us. We're dealing with a cubic that has a negative in front of us, so it's going to come up from here and go down to here. That helps us. We're going to take the first derivative, minus 12x squared plus 36x, and we discover, oh, those both have x's in them. I can take a minus 12x out of the first one, and I get x minus 3 as the leftover derivative, which means if this is the first derivative, if I set it to 0, I discover there's going to be two maximum mins. One is at 0, so I already know it's 0 comma 3, and one is at 3, and when I plug that into the equation, 3 cubed is 27 times minus 4 is minus 54 minus 108, and then it's plus, let's do it up. Let's just do it by hand. 3 here. Positive 3 becomes 27 times minus 4 is minus 108. Then the next one is 9 times 108. I should try to keep it somewhat clean. 9 times 18 is positive, let's see, 90, and 9 times 8 is 72. So that's 162. And then plus 3. So 108 minus 108 plus 62 becomes 54, plus 3 is 57. So I discover 3 comma 57 is another one. Boom. I now have a min. I now have a max. I know that it mins at 0 comma 3. So it comes down at 0 comma 3. It's going to go up to 3 comma 57. Then it's going to come down, which means I'm going to have an x-intercept around 4. And because my factors for these were clean, let's take a second derivative and figure out where the inflection point is. I get minus 24x plus 36. which means x at 2/3 is the, no, 3/2, 1.5, is the inflection point, which makes sense. It's somewhere, it's between 0 and 3. So that means the inflection point's going to come in here somewhere. If I put it into the formula, it's going to come out as, probably 3 comma, halfway between 57 and 354, 3 comma 27 around. Let's just see quickly if we came close on all this. So we get a minus x cubed minus 4x cubed plus 18x squared plus 3. So there's the min and max is discovered. I'm going to just find out where the inflection point is. 1.5 comma 30, nailed that. And so where's the, yeah, just to the right of 4. So pretty much nailed it pretty quickly too. So I'd say always do the second derivative to see if it's clean before you try to find factors of before you try to find factors of the formula, which can take you forever by hand. Okay, so this is interesting. You should notice right away, intuitively, this will have a horizontal asymptote of 0. But the whole thing is raised by 3, so it'll probably have a horizontal asymptote at y is equal to 3. But I want to show you that you can put all of this equation as one line, and it'll help you understand other things about it, possibly. If I was to add that as a fraction, I can't do it until this one as a fraction has the same denominator as this one, which means I have to multiply it by this over this to get it on the same fraction, which means I'm left with that plus 1 all over that. Now, I'm generally going to leave it like this for solving the problems. But if I was going to find more to better understand a graph, sometimes it's important to do this. If I was going to expand the bottom, I get x squared plus 4x plus 4. If I'm going to expand the top, I get 3x squared plus 12x plus 13. This also clearly shows that the top clearly has the same exponent as the bottom, and why the horizontal asymptote is indeed 3. Because when you factor out x squared from everything, you're left with a 3 over a 1. You could also well, no, let's just leave that like that. But I just kind of wanted to show you that these are the exact same formulas. They're the exact same graph. Okay. Let's get to taking first derivatives. Well, let's get to identifying asymptotes first. We've discovered also that when I put a minus 2 down here, I get a 0. So I've discovered a horizontal asymptote and a vertical asymptote. Now you should also make it equal to 0 to see, or sorry, equal to 3 to see if it ever crosses the horizontal asymptote. So first thing, you make the formula equal to 3. You bring the 3 to the other side. You get this is equal to 0. You multiply both sides by x plus 2 squared over 1. You get 1 is equal to 0, which clearly makes no sense. Therefore, it does not cross the horizontal asymptote. Useful information. Now, if I draw it, you should also go back and say, does the original formula cross the y or x-axis? And that's where this formula is more useful than this one, because figuring it out becomes quite a nightmare. I mean, you could do it. You do 1 over x plus 2 squared is equal to minus 3. You bring that up top and you solve it. But you're going to discover that it is essentially going to be the same as expanding this. Let's do it this way to see what happens. So when does this cross the x-intercept? When y is 0. When you bring the 3 over there, it's when this whole thing is equal to minus 3. When you expand it, you get, and I'm just going to keep the original formula, you get minus 3x squared minus 12x minus 3 is equal to 1. When you bring the 1 over to the other side, or sorry, minus 3 times 4 minus 12. When you expand it to the other side, when you bring the 1 over, you get minus 13. When you try to make that equal to 0, you can see you've got to factor out the minus 3 first, or minus 1 out first. It's easier on this expanded side just to see when that is equal to 0. You would probably jump straight to your quadratic formula and say 3, 12, and 13. You can also create your own quadratic formula in an Excel sheet. We discovered that we only get imaginary numbers, which means this thing will never cross the x-axis. Useful information. So now we know it's not going to cross the horizontal asymptote. We know we have a vertical asymptote here. We know we have a horizontal asymptote here. We just need to see what it does on the left. We know it doesn't cross the x-axis. That's some interesting information. So it's either going to do something, we really can't be on this side. It's probably going to be both on this side, since it doesn't cross the x-axis. So my guess right away is it's going to be something like that. But we need to have more information. What happens when this becomes negative infinity? It obviously stays positive, and it stays 3 over 2. We know it doesn't cross the horizontal asymptote. What happens when it's right close to minus 2? Let's take minus 3. So you get minus 3 plus 2 becomes minus 1 squared, 1. 3 plus 1 becomes 4. So right here at minus 3, we get 4. So we know it's positive. Now what happens when we take 1? We get 1 plus 2. Or no, so what happens when we take just to the right of minus 2? Minus 1. We get minus 1 plus 2 is minus 1 squared. It's 3 plus 1 again. So we can see we have a 3 comma 4 on this other side. Almost immediately tells me, since I know it doesn't cross the horizontal asymptote and doesn't cross the x-axis, that this is what we're dealing with. So let's put it 3 plus 1 over x squared. X plus 2 squared. And let's put in our asymptotes. And there we go. Pretty much as predicted. You can also set this to equal to 0 to see if it ever comes up with x-intercepts. It doesn't. Oh yes, you should also take the first derivative. Since I already knew this is how it's going to behave based on the values, you could also take the first derivative. The first derivative of 3 is 0. This x plus 2 is the same as that. Taking the first derivative by the chain rule is minus 2 to the minus 3 times the derivative of the content, 1. So I end up with minus 2 over x plus 2 cubed. This is the first derivative of this. It's very clear to me that when I set it equal to 0, it doesn't exist because this goes up and becomes 0. Minus 2 equals 0 is all I have left, which doesn't make sense, which means it has no max or min. Since the derivative can't equal 0 in any way, shape, or form, we know there's no max or min, and there's no need necessarily to take a second derivative, because if there's no max or min, there's probably not going to be an inflection point, because it means it never changes direction. You could take the second derivative if you want. So the second derivative of this becomes 6 over x plus 2 to the minus 4, or to the plus 4. It's also clear when I set that to 0, it doesn't come out. It ends up being 6 is equal to 0, so there's no inflection point. So there's really no need to take a second derivative. So once I take first derivative, second derivative, once I took first derivative, I knew there was no inflection points. I'm not going to do this cubic. It should be very easy to figure out. I would take the first derivative and just see if it comes out clean. So the first derivative is 4x cubed. Minus 12x squared minus 16x plus 40. Oh, the first thing I would do, notice they all have x. Factor out an x. That's the tricky part here. So you get x cubed minus 4x squared minus 8x plus 48. So it becomes x times a cubic. And that immediately tells me it goes through 0, 0 also as a point. So that helps. When I take the derivative of the main thing, I get 4x cubed minus 12x squared minus 16x plus 48. When I take the second derivative of that, I get 12x squared minus 24x minus 16. I can clearly take a 3 out of each of them. No, at least a 2. And another 2. So I can clearly take a 4 out of each of them. 3x squared minus 6x minus 4. I'm doing it pretty quickly. I can see if minus 12 can possibly add up to minus 6. I don't believe it can. Can I multiply minus 12 by anything? 6 and 2 plus 6 minus 2? No. I don't think so. But you can throw this second derivative, 3 minus 6 minus 4, into the quadratic formula to see if you come up with imaginary numbers. No, you don't. So that means it came up with 2 inflection points, which means there's going to be some max and mins on this. Notice it's not clean, which means I can probably find clean factors of this. So just without graphing it, one thing I could do, I know it goes through 0, 0. So I know one of the factors is 0. So really I only have to factor this. And one thing I could do quite quickly is just take the leading coefficients, make sure I got them right, and just try a couple numbers really fast. Nope. Now I'm going to try minus 1. I'm pretty sure minus 1 isn't going to do it either. Nope. And from that 48, I can immediately tell it's somewhere it's going to be like 2 or higher. I hate when it does that. It's going to be higher than 2. No, close. Let's jump right to 3. Okay, I'm going to go try to 4. I should have even tried 3 because it's not a factor of 48. Nope, but I am going to try -4. I think I got it here. So you discovered right away that -4 is a factor. So that means as factors I get x minus 4, and I'm left with x squared minus 8 plus 24. And actually that's plus 4 because I used minus, didn't I? So making sure, -4, -8, plus 32, 24. I didn't do this last one correctly, so it's not. I'm pretty sure there's a clean factor in here, so I'm going to just throw up the equation. I know I said I wasn't going to do this, but -4x cubed. I'm going to just turn off the drawing so I don't see it. And I'm just going to take, we know that when it's 0, 0, 1, 3, 4, 5, nope, -1. Oh, so there are no clean factors. Okay, so I screwed that up. There were clean factors of the first derivative. Okay, so I screwed up the first derivative. So here's the first derivative. And if I do the synthetic division with that, I quickly discover that -2 is a factor, and -8, you get -20, you get 40, you get 24, -148. So then you end up having this as a factor, and you end up having 4x squared minus 20x plus 24x, but you can take 4 out of that. So you can put 4 in front, and you're left with x squared minus 4x plus 6, and it's quite clear that it's -2 minus 3, no. Or this is a 5. So you get -2 minus 3. And since those are all clean, and those are all max points, which means there's going to be a max point at 2 something, at -2 something, at 2 something, and at 3 something. Once you plug those into the equation, you, since this is a cubic facing up or normal, you know the first one's going to be a min point at -2. The next one at 2 is going to be a max point. And then it's going to come down it's going to be imbalanced a little, come down to 3 and then go up. Now you would plug those into the original equation to get the values. Let's just try something like that. I don't know if it's going to do it. And then you would find your points of inflection as well, and then you would join them. And sure enough, it does a weird little wiggle there. And that's what you get. And it goes through 0, 0. The inflection point on this one is going to be between -2 and 2, so I suspect the inflection point is going to be 0. But just to make sure, one of the inflection points, there's 2 inflection points. I'm going to set the second one to equal to 0. And sure enough, no, the inflection point happens there, and there is our quadratic showed us. So I got fooled by this because I failed to realize the... But notice that when the min-maxes are clean, the x-intercepts are not clean. Okay, let's go on to more important ones. Something like this. I want to point out the key features of it. One, you have a value up here that's less than this. This is a difference of 2 squares. So it's really this. But you also have a value up here that's less degrees than that. So you're going to have y is equal to 0 as one of the horizontals. You're also going to have x is equal to 5 and x is equal to -5 as 2 of the asymptotes. And you can see we're taking, first and second derivatives is going to get very complicated with this. So I'm going to first see if it ever crosses the x-axis when equaling 0. This disappears. When x is 0, it crosses the x-axis. So that means we go through 0, 0 as one of the points. When x is 0 here, well, we've already determined, but sometimes you would make x is 0 to see where it goes through the y-axis. But we've already determined it goes through at 0, 0. You should also see if, which means it does cross the horizontal asymptote as well. It's very symmetrical, you should note, because the vertical asymptotes are equidistance from the origin. So it should make it up here, x is equal to -5. X is equal to 5. You should also have one on the x-axis. Y is equal to 0. But we know it's going to cross it. And it's either going to do that, it might do that, just touch it, you know. But my guess is it's going to do that, which means taking measurements here and here to see if they're positive or negative is really important. We should also look at what happens when it's negative at infinity. This becomes negative, this becomes positive. So it's going to be on the bottom side of the asymptote. Now, since I know it only crosses the asymptote once here, I already kind of know it's going to be here. When it's positive infinity, this whole thing becomes positive. So I know it's going to be something like this. Only mystery for me is going to be in the middle. So if I look at -5 and 0, and I take something just to the left of -5, like -4, -4 squared becomes 16, and -25 becomes -9. -4 up here becomes -8. So I can see it's going to be positive, but it's very small, so I should be very careful about my values and try again. So let's try -3. When it's -3, the top value is going to be -6. When it's -3 down below, it's going to be 9 minus 25, which is definitely -16. So it's going to be 6 over 16 or 3 over 8. So it's a very minuscule but positive value. Now I'm going to try over here when, let's say for 4, or actually let's just take 1. 1's easy. We get 2 up top and -24 at the bottom, which is a very tiny negative number, right? Which tells me my middle, I got it wrong. It's going to do something like this. Now, this is a case where you should take very close to -5 and a 5 to see that it goes way down to negative infinity y, which it should. So again, I'm going to put in the graph without the graph showing and get 2x divided by x squared minus 25. And I'm going to put in a value of like minus 5.0001, which is just to the left. And it goes down to negative infinity. Now I'm going to do negative 4.999, which is just to the right. And it goes way up to positive infinity. So that means, and you're allowed to do that on a calculator, that means we are 100%, if that's the Cartesian graph now, and I take black as my asymptotes, it is 100% doing this, and I'll use green for my graph. It's 100% doing that. And finally, you should take just to the left of the right asymptote, which is 4.99. And I see it's negative infinity. And just to the right of it, which is 5.001, which is positive infinity. So that means for sure I'm also dealing with that. And you always want to double check your values. Now, I happen to know that if I take a first derivative and second derivative, it's going to indicate that that's a max, but the second derivative is going to indicate that's 0. So I don't know if it's worth taking the derivative, since I know the behavior of these graphs from experience. And the more you graph them, the more you will. But if you decide to, the process is a little bit difficult. You must find out the derivative of 2x, which is 2. You must find the derivative of x squared minus 5, which is 2x. Then you must square the bottom and keep it as a denominator, which surprisingly won't have a big factor on finding when it equals to 0. It actually won't do anything except influence the next derivative. So that whole denominator has to be squared. You have to take the first derivative and multiply the denominator and multiply it by the first derivative, which is 2, right? Oops, yeah. So you're going to get 2x squared minus 50. And then you have to subtract, all in brackets, the second function multiplied by the derivative of the denominator, so minus 4x squared. So when you get 2x squared minus 4x squared, you're left with minus 2x squared. So you're essentially left with minus 50 minus 2x squared. Or rearranged, minus 2x squared minus 50. When you set that to 0, you discover, and I hope I got the derivative right, you discover 50 over minus 2 is equal to x squared, and you realize, no, there's no max. Because you can't have x squared equal a minus number. So again, you can figure it out using Desmos if you want. When is f of x, the derivative, equal to 0? And it's saying never. And when is the second derivative equal to 0? And it's saying, it's 0. So that tells me there's a slip and slide there. Let's turn on the graph. There we go. Behaved exactly as I drew it. And can even put in your vertical asymptotes if you want, and your horizontal one. Now, obviously, this is all about derivatives, so they want you to practice the derivatives on these. This one's actually going to be a little bit easier for an obvious reason. I want you to notice what happens to the bottom when you factor out x. It becomes x minus 4, right? Which makes the two possible values of 0 at the bottom much clearer. So you're going to have a horizontal asymptote when x is equal to 0, or vertical rather, and when x is equal to 4. The whole thing also will have a horizontal asymptote at equal to 0. And when you set it to equal to 0 to see if it crosses, you end up with 1 is equal to 0, so it doesn't cross. So that's important information. When x is 0 here, we've already determined that y is, that there's an asymptote. So that means it's not going to have a y-intercept. Or, yeah, it's not going to have a y-intercept because x is equal to 0 is an asymptote. So let's get on with taking the first derivatives and see what we get. The first derivatives is this graph is the same as x squared minus 4x to the power of minus 1. That's all it is. That's the same graph. When I take the first derivative, I get minus 1, and the inside the brackets comes to the negative 2, which means it goes down to the denominator squared. But then I have to multiply by the derivative of the content, which is times 2x minus 4. When I multiply that by minus, I get minus 2x plus 4. So that's the numerator now. And the bottom simply becomes the same thing, but now it's squared. You can see that the derivative, especially when we go to the second derivative, is going to get more complicated. However, when I set this equal to 0, I only care about the top, and I get minus 2x is equal to minus 4, or x is equal to half, which means there's a max or a min when x is equal to a half. So that means there's a max or a min when x is equal to a half, and that's important information. So let's check that out and remember that. When x is 0.5, something happens. Well, let's see if we can find the y value here. 0.5 squared is 0.25. Minus 4 times a half is minus 2. So you get 1 over negative 1.75. If I take my calculator, and I'll just confirm it with my calculator that I got it right, 1 divided by brackets 0.5 squared minus 4 times 0.5 equals close brackets. So it says negative 0.57. Let's see if we got that. 1 divided by 1.75. Yep, that's we got our calculation correct. So that means this is the x value, or the y value. When x is 0.5, there's some sort of max min going on. And it repeats. That whole section here is repeating. Which means really there's a fraction I could represent it as, but I'm not going to bother. Okay, so that was the first derivative. We need to know if that's a max or min. Well, let's just do our drawing what we have so far. We know there's a horizontal asymptote that it doesn't cross on the x-axis. We know there's a vertical asymptote as well on the y-axis. And we also know there's another asymptote here. Since it doesn't cross the horizontal, I know that this middle part must do something like that, which means the other sides are probably opposite. So let's look at negative infinity. Use this here. When it's negative infinity, it's quite clear that this becomes positive infinity, which means it's going to be on this side. When it's positive infinity, it's quite clear it's going to be here. So now all I care is about the middle. So I can just take like 1. So if I take 1, I get 1 over 1 minus 4, which is 1 over negative 3, which is negative a third. Which tells me I'm dealing with something like this, because it doesn't cross here. And right here, I'm going to have a max point. And boom, you're pretty much done. You could, we know there's no min here, so it doesn't start going up or anything like that. It doesn't cross it. Sometimes these do cross the horizontal asymptote and you end up with min points there, but not in this case. We discovered the first asymptote is this. Now, technically, they want you to take the asymptote and plug in this value of x to see if it comes out negative or positive. If it comes out negative, it's a max point. If it comes out positive, it's a min point. However, to do all that, to get that, it's much easier to take your graphing techniques and figure it out than to take a second derivative just to figure out a min-max point. There's no inflection point either because it doesn't change directions. It's always curving like that. So let's see if we got this right. 1 over x squared minus 4x. 1 over x squared minus 4x. And we'll get rid of the old stuff. We'll keep that. We'll do x is equal to 0 for one of the asymptotes, and x is equal to 4 for the other. And we'll just zoom in a bit. Great. We're going to put in 0.5 comma f of 0.5. Oh, I got the max wrong. So that means I did the derivative incorrectly. Just goes to show you how easy it is to do the incorrect derivative. It's clear to me that the 2 is the derivative, or the max point, but I'm going to go back and determine what I did wrong. So I did this part right. This is indeed x squared minus 4x to the minus 1. Which says chain rule. I have to multiply the minus 1 in front of the brackets. And I'm going to be x squared minus 4x to the minus 2. And then I have to take the derivative of the brackets. And keep in mind this is x squared here, which becomes 2x minus 4. When I multiply that by minus 1, it should become minus 2x plus 4. Oh yeah, I totally screwed that up. And all of it over this squared. And not negative anymore because I put it back down into the denominator. Like that. It's clear to me if I make this equal to 0, and you just ignore this part, that this, I totally screwed up, is x is equal to 2. Which means I should have put in 2 into here, which is 1 over 4 minus 8, which is minus 1 over 4, which is minus 0.25. So I screwed that up, and that's okay. And we've got to do f of 2, not 0.25. There you go. So you can see how taking these derivatives of these rational functions is the danger zone. And usually I screw them up because I rush. These next ones, I'm not going to go too deep into them. Okay, and I know I say that, and then I go deep into them. Except to figure out, what can x be? Well, we only have one asymptote. And that's when x is 0. When will this ever equal to 0? When x squared is equal to 2 over 6. So there's going to be 2 x-intercepts, which is the square root of 2 over 6, and the negative square root of 2 over 6. So I'm going to just punch this into the graphing calculator, but turn it off. So I've got 6x squared minus 2 over x cubed. Over x cubed, just over x cubed. So I'm going to just automatically put in my asymptotes. And I'm going to put in, make that red. And I'm going to put in, what's my horizontal asymptote? So the higher value is equal to, is lower than the bottom value, so it's equal to 0. So there's a horizontal asymptote there. Another step I need to do, now I've also said I've determined that the x-intercepts are negative square root of 2 over 6, comma, f of negative square root 2 over 6, and the positive version of that. So those are going to be the two intercepts. So there's probably going to be a max or min. Because my guess right now, if I'm going to, oops, if I'm going to grab an image of them, my guess is it's going to do something like this. Cross and hug, cross and hug, creating a max and a min here that are probably identical but opposite signs. So that's a big key there, just knowing that because it crosses, it's probably, because it has to hug the asymptote. When it crosses, it gets below the asymptote, and then it's going to come back up. I don't know which side it crosses. You have to take values to the right. You know, you'd have to take 1, 0.5, minus 0.5, and negative 1. So let's start by doing, actually let's start by seeing if it, what was the other thing I was going to see? I was going to see if, because I figured out the x-intercepts, and I know there's a max or min. Oh, when x is 0, there's no y-intercept. And we know there's a horizontal asymptote, and we know it crosses. I was going to do something else. Oh, I was going to, no, I just did that. So I guess we go to derivatives, because we need to figure out the max or min. Oh, I know what I was going to do. I was going to figure out 1. So negative 1 becomes 6 minus 2 over negative 1, which is negative 4. So that means negative 1 here is at negative 4. So that tells me it's going to dip quite low and then climb up through negative 1 and 4. And if I take, like, just to the right of that x-intercept, I need to know what square root of 2 over 6 is. It's 1/3. And square root of 1/3 is 1 over square root of 3rd. And if I take my calculator and take 1 and divide it by the square root of 3, I get like 0.57, yeah. So I need to take 0.1 as one of these values. Negative 0.1. So it's obviously going to be negative, because it's, oh no, it still might be negative up here. Okay. I think it's going to be positive though, because it's got to come through and go up. So if I take negative 0.1, I get 6 times positive 0.01, which becomes like negligible. So the top number becomes negative. And if I take 0.01 down here, it stays negative 0.001, which brings this top number back up. So it's clear that I'm going to be way up here. So now I can even certify that it's going to do this. And it's going to do this. Now all I need to do is find those max and those mins, which means derivative time, right? Okay. To find derivatives of quotient, and here's, I'm screwing these up badly, right? You need to find the derivatives of the denominator. and you need to find the derivatives of the numerator, you need to square the denominator. So on the bottom I'm left with x. What's the square of cubed? X to the 6. I have to multiply the original denominator by 12x. So I'm going to get 12x to the 4. Now I have to subtract whatever I end up in the bracket. So that's going to be the second function times 3x squared. So I get 18x to the cube minus 6x squared. So I got 18x to the 4 minus 6x squared. And that means that minus is going to make this negative and this plus. So 12x to the 4 minus 18x to the 4 is going to be 6x to the 4 minus 6x to the 4, an important distinction. And then plus 6x squared. I put 4 here, but it's not. It's squared. So I get this. Minus 6x to the 4 minus 6x squared all over x to the 6. Well, if I cancel out, this comes down to 4. This comes down to none. Like that. And this one stays 4. Becomes 4. Essentially, I've canceled out x squareds on all of them. I can also take a 6 out of that first one. A negative 6. And I'm left with x squared minus 1 all over this. So that's my first derivative. It's clear to me, if I set this equaling to 0, the bracket here is what dictates this 0, which means that when x is the square root of 1, which is 1, or when x is the negative square root of 1, which is negative 1, that will be my max and mins. Since I know the nature of the graph, I don't have to take the second derivative, although they would want you to. So when it's 1 up here, I get 6 minus 2, I get 4 over 1. On there, I accidentally found the max mins before. And when I take negative 1, I'm going to discover that it's negative 1 comma negative 4. Okay, so that means on this graph, negative 1 comma f of negative 1, which is actually going to be negative 4, is going to be the min point. And 1 comma 4 on the other side is going to be max point. And as I said, I'm predicting that it's going to look like this. Oh, not going to cross again. Let's see. There you go. Now, they would want you to take the second derivative and then plug in 1 to see if it's positive or negative. I mean, but we don't have to if we correctly mapped out our graph. And the more you can label, the happier your teacher will be. Remember that. The more spots you identify, the more marks you're going to get. So you could just go ahead and plug away spots if you were lost. You do x is equal to 1, x is equal to 2, x is equal to 3. Let's look at, that was this one, right? Let's look at this one because it has some factorable things in the bottom. And I can't spend much longer. I have to run. I'm supposed to go pick up something, but I'll do a couple more. Okay, it's clear in the bottom can be factored to x plus 2 and x minus 2. and that it does not cancel out with the top, so we get tons of information here. First bit of information, when x is 0, you get 3 over minus 4, which means you have the y-intercept. When x, you have a horizontal or vertical asymptote at x is equal to minus 2 and x is equal to 2. The factors above, the terms above are lower than the terms below, so you have a horizontal asymptote at y is equal to 0. Does it ever cross the horizontal asymptote when this is equal to 0? Yes, it does, when x is minus 3, which means you also have a point where it crosses the horizontal asymptote at minus 3 comma 0, which is the x intercept, right? So that's a lot of information. So if I'm going to draw it, and I'm going to put my asymptotes in, x2, x minus 2, y0. I also know it crosses here at minus 3 comma 0. I also know I have a y-intercept. Here's an interesting spot, because I know the y-intercept is 0 comma minus 3/4, and I know it only crosses the horizontal asymptote once. I automatically know this graph is going to be like that. Because they're symmetrical, I also know that that's probably going to be the max point. That is probably going to be the max point, because that's right on the x-axis, which is exactly in the middle of the two asymptotes. And all I would have to do is figure out if it's crossing here. Since I know it's not crossing on the other side, there's something weird going on the other side. Because the only time it crosses the x or the horizontal asymptote is on the left side here. So there's probably a min point here and a max point here, or possibly, unlikely though, a max point here, a max point here. But it also means on the other side it's behaving. So you want to take values, and you definitely want to take the derivative, because there's going to be two min or max points. But you can see how much information we got already. Let's have a look at what happens when this thing is positive infinity. You get positive infinity over infinity squared positive. So it's going to be hugging 0, because infinity over infinity squared is 1 over infinity, which is hugging on the positive side, because it came out positive. Since we know it doesn't cross the x-intercept, we know it does that. Let's look at what happens, since this is minus 3 and this is minus 2. Let's see what happens at minus 2.5. I get minus 2.5 at, becomes plus 0.5. And minus 2.5 here, minus 4, so minus 2.5 becomes positive. Minus 4 is positive. And when I take 0.5 and divide it by 2.25, I get, where's my flip? 0.2222. So it still is not telling me enough information. I know it's positive, but it's still hugging here. So it's weird. I'd have to take right beside the asymptote. So I'd have to make like minus 2.0001. When I add 3 to it, I get minus, or I get positive, like 0.99, almost 1. When I take 0.0 or negative 2. Negative 2.001. When I take negative 2.001 and square it, it becomes positive. And and then when I subtract 4, I get a tiny, tiny number, which means 1 divided by a tiny, tiny number is way up here. So it's going to come down. All I need to do is figure out the min and max points. So that's what it does. So that means I need to take the derivatives. So I'm going to get rid of this graph, and hopefully I was right, otherwise I look like a fool. And I'm also going to put this into Desmos, right, just to make my life easier, but without the graph. Desmos is a fantastic learning tool to verify answers without going to the back of the book, right? Because sometimes the back of the book's wrong, or you misread it, or whatever. Okay. Got it. So we know a couple things. We know minus 3 comma 0. What else did we figure out? Halfway between, we know 0 comma negative 3/4. We know x is equal to minus 2, x is equal to 2, y is equal to 0. So we know that. And we also know, like, it goes way up here. We didn't figure out, yeah, we did, and it goes way up here. So now we have to figure out the derivatives. So the derivatives say, I need to figure out the derivative of the denominator and the derivative of the numerator. It's quite clear the derivative of the numerator is just 1, which makes our life easy. Derivative of this one is this. And I'm going to square the bottom, which fortunately doesn't have that big of a roll for us. And I'm going to take the bottom and multiply times the derivative of the top, which fortunately is just this. And then I have to subtract in brackets the function up top times the derivative of the denominator. When I multiply those out, I get 6x squared plus 6x. All in brackets. The brackets are important because this minus here applies to both things. So x squared minus 6x squared clearly becomes minus 5x squared. Then it becomes minus 6x, and then it becomes minus 4. So I'm left with this up top. Hopefully. Which means if I can find factors for up top, I can figure out the max and the min points. So looking at the top, I'm looking for a number that multiplies out to 20 and adds up to minus 6, which is almost impossible. We should also actually, you never want to have a minus in front. So we're going to take a minus out. We're going to put a minus in front here. And that makes all our numbers positive. So we're looking for a number that adds up to 20 and adds up to 6, multiplies out to 20. And you take like 4 and 5, and you can see that it's going to be very hard. So there's a good chance, as always, that I screwed up the derivative. So we're going to look at, and actually this is another great little thing here, Symbolab. So whenever you want to confirm that you got the right derivative, x plus 3, x squared minus 4, you can say, find me the derivative of x plus 3 divided by x squared minus 4. And you can just go ahead and do it, and it should tell you if you got the right thing. And look at that. The only thing I screwed up, it looks like I got the subtraction wrong. So it's not 5x. So it's a good thing I checked. That is not the derivative I got. So let's see where we messed up. That's the actual derivative. So let's try again. You can see how rushed, when I rushed, how screwed up I can get them. But I had a feeling I got the wrong one based on the result. So again, you have to figure out the derivatives of these two things. The derivative of the bottom one's easy enough. It's 1, and it's 2x. You know that this is going to be the bottom, just from the quotient rule. You know you've got to take the bottom derivative and multiply it by 1. So that's all of that. Minus the second function, which is this, in brackets, times 2x. Oh, I totally screwed that up, eh? I said 6x. Stupid. It's clearly that it's 2x squared plus 6x. And when the minus is applied to it, it's minus 2x and minus 6x. And it's clear that I should have ended up with not minus 6x squared like the idiot I am, but minus x squared minus 6x. I should have ended up with this, quite obviously. And that just goes to show. Now, you should still take a minus out of it, and you're left with x squared plus 6x plus 4. And you should ask yourself, what number multiplies out to 4? That adds up to 6. And you should quickly see that you can't really do it. So you should take the quadratic and put in 1, 6, and 4. And if I got that wrong, no, it does indeed come up with 2 numbers for me. Both of them negative numbers, which is interesting. Which tells me that at negative 7.6, which is just to the left of 0, so my maximum was not at 0 as I suspected, and at negative 5.23 there are min and max. So that's going to be one of the min points, very close to the axis. And the other one's negative 763. And so right away, ooh, okay, yeah, that makes sense. So that means it's actually going to be slightly bumpy in the middle and cross through the y-axis there. So let's have a look. So again, I'm saying it's going to come down, cross the y-axis, and then hug. And on the right, I'm just saying it's going to stay above. Okay, got it. The only thing I screwed up was the max mins, and that's from getting the derivative wrong again. So there's the min point right there. And notice you had to do the quadratic function to find the max min points. That's it for now. I will try to do a couple more, but I think this one will be more challenging as what's going on with it. Because visually it's hard to understand what's going on. And I'll do more later.